Welcome everyone to SAT Math Question of the Day. Yesterday, not good. We made this really great recording and I didn't have my sound on. So, you didn't get one yesterday, but today we'll do the same problem. Okay. Anyway, welcome to SAT Math Question of the Day with Professor Emeritus Seth Chaiken, University of Albany, and Joel Chaiken. We're here to go over how to approach SAT math questions. And here is our question of the day. And it is from a non-calculated section. Please pause and then come back and then, let's see how it's done. So today I'm going to do this problem as if I was doing it without knowing how to do it, like live, like yesterday. But, okay, let's go. Okay, so here we have these two things, and these two functions or things, I'm calling them things. How many ordered pairs satisfy systems of equations? So there are different, I always into this different modality of thinking. And sometimes it's better to think algebraically, sometimes it's better to think graphically. Here, it's better to think graphically. Now, when you have, what they're really asking is how many places do these two curves or graphs or functions cross when you graph them? That's essentially what they're asking, is how many places do they have a copy? It's this way, if it's an equation, you could just graph the things, and where they cross, that's the solution. So let's think this through. So let's do it let's get a feeling for this. So this one you have to get into y equals mx plus b form. So this would be 2y is equal to x minus 5 divided by 2 divided by 2 divided by 2. So this is 1/2 x minus 5 over 2. So that's, you go down like 2.5, and it's got a gentle slope of 1/2.
Oh,
reasonable,
okay.
reasonable. Now this is a quadratic, which is going to be a parabola. So yesterday I started foiling it out. Let's see what it is. 2x minus 3, x plus 9, and around here I realized, whoa, wait a second, it's a parabola. We know the roots of the parabola, and the roots of the parabola is when y is equal to 0. When y is equal to 0, we can tell immediately those numbers on the parabola. So I stopped doing this because I realized there's a better way to get a sense as to what this parabola looks like, which is to look at the roots. So we know the parabola goes at x is equal to -9 because that sets this thing equal to 0, because this is x and this is y. This is y. This line here is y equals 0. And then also look at this. I guess 3/2. X is 1.5. 1.5, or 3/2. And because the x squared is positive, it's an upward parabola. So if it's an upward parabola...
Wait. Oh, okay, good. Excellent. Okay.
Yeah, now the trouble is that I don't know. I don't know yet if it's that type of parabola or if it's this type of parabola. Oh my God. If it's the blue one, then they don't cross at all. And if it's the black one, then they cross at 2 places. Okay.
And it might even be a parabola that's tangent to the line, in which case they cross at one place.
No, you mean no, but it's not. But it can't be tangent to the line because this is a straight line. If it's tangent to the line, it's a weirdo parabola. It's a parabola.
No, so it could be tangent.
No, it can't.
Yes, it can.
Okay.
Imagine the parabola is slowly morphed. The blue parabola is slowly morphed into the black parabola. When it first touches the line, it will be tangent.
Oh, right. Okay,
tangent will be the tangent will be the line with the slope of 2/3.
Fine. Okay, Seth's right.
So that's why. For a general problem of this form, all three.
Okay.
All the first 3 solutions are feasible.
Fine. Okay. Fine. Come on. Let's not break the mojo. Let's talk about that stuff later.
Good.
Let's just.
But the point is, you need to need to figure out whether the parabola is like the blue one or the black one.
That's right. So, yes, I said that. Okay. So what do we have to do? We have to figure out where the vertex of the parabola is. That's the goal. So how do we get the vertex of the parabola? Then I realized, the vertex x value is in the middle. Parabolas are symmetric. So if we find the midpoint between -9 and 1.5, then that gives us the midpoint of the parabola. Okay, if we know the midpoint to the parabola, then we put that midpoint into this function, and that tells us how far down the parabola is. So then I made an approximation. So what's the average between -9 and 1.5? Negative 9 plus 1.5 is like 7.5. 7? No. No. What am I talking about? It's the
7.5. Negative 7.5.
No. But
then you have to divide it by 2.
Yeah. You have to divide it by 2. So
it's negative 7.5 divided by 2.
Negative 7.5 divided by 2 is like -3, right? Something like that. 3, 4, 6, 4. 4 is 5. Yeah, it's about 4. It's about -4. So the point is that you don't actually have to know the exact number. You just have to know that it's like around -4. See, that's about 5 this way and about 5 this way. It's close enough. Wow, yesterday I did 5.5, so I was wrong. But it doesn't matter. We're going to throw the -4 in here just to get a sense as to where that parabola is. So what is 2 times -4 minus 7 is -8 minus 3, which is -11. And then -4 plus 9, -4 plus 9 is like 5. Minus 55? Are you kidding me? Minus 55? That's like down here. That's ridiculous. Which means the parabola goes here. So it's very obvious. It's very obvious that it crosses in 2 places. Very obvious. Right? Because this is so far down. Notice I didn't have to really know what the number was. I just had to know approximately where it was. So you can approximate everything. I never really got the midpoint. I never really got that. So that's that. So that's an important part of the question. You don't have to waste your time doing exactly. You just have to do it approximately in cases like this. If you're lucky. If it turned out that it was too close, oh my God, that would be a problem. It would take 5 years to do. But it's not. So you do approximation, so it looks like the answer is 2. So then, Seth, you sort of like that way of doing it, right?
Yeah.
And then we decided, how would you do it algebraically? So I think probably I did this problem right now it's 7 minutes into the video, but I was interrupted and I talked a bit. So maybe you could do it in 4 minutes. So this is a long problem. You would want it. This is why you bank up time on the shorter problems, because you're going to have to spend some time doing this problem.
Okay, well, let me just, for the benefit of our audience.
Okay.
Let's see, we did minus, so this big blue dot, which is near the vertex of the parabola, has coordinates, what do we say?
Negative big.
Negative
no.
4.
No, it's not -4. It's about -4.
Approximately -4. Approximately -4 and approximately negative 55.
Negative big. But it has
negative 55.
It also has to be approximately negative 55.
Yeah. Right.
Yeah.
So, and the line is well above that. Okay.
I like
this. I like this. I like this approach. Sure.
So now yesterday, we tried to do it algebraically, and it was a mess. But today we'll also do it algebraically, and it won't be as much of a mess because we already made the mistake yesterday. So let's just clear the whole thing. How would you do this algebraically? So what
we would do is first. Well, the idea to do it algebraically is the standard idea for solving systems of 2 equations with 2 unknowns. That idea is to eliminate one of the unknowns, producing an equation in one unknown, solving for that unknown, and then if you want to know the other one, you back substitute and solve for the other unknown using one of the equations. Right. But the problem is not to find all of the solutions, but to figure out how many different ones there are.
Right.
Okay? So one choice for doing the calculation is to eliminate x To eliminate x, we could take the expression from this equation. X is specified to be equal to this function of y. You take this value, this expression in y, and substitute it for each of the x's,
right,
in the equation below, and we will get an equation of the form y equals 2 times, well, what you put in for x.
Right.
Which I won't write in because
right.
minus 3. And the whole thing is multiplied by the same expression obtained by rewriting x plus 9.
Right. Okay, Seth, so can I do it yesterday?
This is one choice. So x. So here we put 2y plus 5 into here, and the same expression, 2y plus 5, into here, and do a lot of arithmetic.
Okay, so Seth, can we do what we did yesterday, where we time this thing and let me do it as fast as I can?
Okay.
Okay? Okay, so we're going to redo this like I did yesterday. So when Seth's not telling you something about how we did it yesterday, so I'm going to start the timer. Right now, believe it or not, we're at 11 minutes and 36 seconds into the recording this thing. So I'm going to do it like I did yesterday. We'll see what happens. Ready?
Okay.
Okay, the first thing I did yesterday is we decided that it'll be great to actually get it in terms of x. So what I did there is I solved for y. Well, we have y. Y is equal to 1/2. So I did 1/2 x minus 5 over 2 is equal to 2x minus 3. X plus 9, and I realized if you're going to be fractions in a quadratic, this is a complete disaster. At this point, I said, well, if you're going to do it this way, just skip the question and get it wrong. And then we realized that in order to not have fractions, we should do it this way. All we care about is whether there are two solutions, and we can tell whether there are two solutions or no solutions or one solution by looking at the discriminant of the quadratic equation. So this is such a disaster. And you don't have a calculator. How are you going to get the discriminant of the fractions? So maybe there's a better chance with this one. And that's how we came to this. So now you have to be really careful. So the way Seth wrote it out was 4y plus 10 minus 3 times 2y plus, I'll just combine this to make 14. Now the way I did it, and Seth's going to say a better way in a second, is I actually sort of foiled it out. And I got 8y squared plus, my God, 14 times 4 plus 2 times 7y plus 7 times 14. Okay? Now, this is a disaster. Like, you're not going to factor this thing. So you're going to have to look at the discriminant. Now, it's a mess. I mean, 4 times 14, you have to sit here. You don't have a calculator. 4 times 14 is I don't know, 56. 56 and 14. 56 and 14 is 70. Oh, this doesn't equal 1. See, I made this is the same mistake I made yesterday. This is equal to y. So this is 8y squared plus 70y plus, what's 7 times 14? I don't know. Can you believe this? 98 equals 1? At this point, I said, look, the numbers are big. Let's do approximations. Seth's putting it there. That's the discriminant. B squared is 4ac. So let's just do it. I'll put it in a different color. So this would be 70. Come on, Zyteboard, no time to freeze. 70 squared minus 4 times 8 times 98. So, is that right? Come on, Zyteboard. This is ridiculous. Okay, so the discriminant is 70 squared minus 4 times 8 times 98. And at this, put the square root makes me happy because we have to realize what's going on here. Now, at this point, you don't have...
The discriminant is what's in the square root.
Yes, right. I know, but I like to put the square root to feel good. Okay, so then, it's not the discriminant. The discriminant is not the square root. Okay, now here, what do you do without a calculator? You approximate, because all we care about is whether the stupid thing is negative or not, or whether it's 0. So what's 70 squared? It's 4,900. Notice we don't really care less. It's actually 69. Do you see that? Do you see how it's really 69? But 69, 70 are close enough for government work. Sorry if you insulted government work. And this is 32 times 100. So all we care about is whether this is like positive, negative, or zero, really. So this is 4,900 minus 3,200. That's a seriously positive number. The square root of a seriously positive number there are two square roots to a serious positive number, because that's the discriminant is a serious positive number, which means there are two answers to this stupid quadratic, which means the answer is 2. So let's see what time it is. 15:36. Yeah, about 4 minutes, right? Yeah, wow, exactly 4 minutes. Exactly 4 minutes. So I think it's a little faster to do it geometrically, but you can do this in 4 minutes. Yeah, you can do this in 4 minutes and get the answer, which is not ridiculously long. It's not like it's 12 minutes. But, and notice I also made all approximations. In no part of this question, graphically or this, did I ever really get an exact answer, because I was wrong on this, and I don't care less about the 98. I made it 100. Who cares? So, approximations really speed you up. 4 minutes, not that bad.
Well, when you did the approximations, you observed that the values you got were very far. The differences were very far from zero. They were big,
big,
and so that suggests that the approximations are valid. Okay. And now on remark, the discriminant is very large, positive, which is a suggestion that which is consistent with the geometry. The geometry showed that the line intersected the parabola over here very far above the vertex of the parameter, which is way down here. The vertex of the parabola, which is way down there.
Right.
So this is indeed a question that is very easily handled by making approximations.
Right. That's right.
And so that may be in the test in this question, because it was a non-calculator.
Right.
A non-calculator question.
Yeah.
Okay.
Yeah.
Yesterday we kind of tripped over each other by also doing the other elimination to eliminate y.
Yeah, but we stopped pretty fast.
Well, we stopped that.
We stopped once you started realizing that you were getting fractions and having to do coefficients with fractions. We just said, forget this. This is impossible. This is crazy. At that point, you literally skip the question. It's just not worth doing.
Well, and then finally, there's another logical issue that that possibly may be a concern. It goes like this: when you did this, you eliminated x. You eliminated x, and got a quadratic equation in y.
Right.
Well, if the system has two solutions, does that guarantee that the quadratic equation in y has two different solutions? Well, the answer is yes. How? Because, and we know that the answer is yes, because if you have two different values of y for which there are x's. Well, if there are two values of y that satisfy the quadratic equation that Joel found, then those two values of y will have x's that satisfy the whole system. Well, then imagine the top equation tells you each value of x for a given value of y that satisfies the equation. In other words, if there's an xy that satisfies the equation, the y would be given by solving this. You plug the y into here, and this will give you the x value.
Right.
Okay. Now, if you plug in two different values of y here, you're going to get two different values of x.
Right.
And therefore that rules out the possibility that the system has solutions where the x values are different and the y values are the same.
Right.
Okay, but in any case, I think the thing you did by drawing by sketching the graphs of the functions that are each defined by the two equations, sketching them approximately but close enough to the exact to tell what's going on is I think is the best way to approach it.
Right. Okay.
And then recognizing the geometric difference, that's germane to this question is whether the vertex of the parabola is above the line, possibly tangent to the line, or below the line.
Right. Right. Yeah.
And when it's below the line, then the parabola sort of it bottoms out at the vertex. It rises as y rises, and it hits the line in two distinct places.
Right. Okay. Yeah. Exactly. That was a perfect summary. I was just thinking while you were talking. I know it's rude to daydream while someone else is talking, but I was just wondering how could they have made this question incredibly easy to be done really fast. Let's do that quickly, and then we'll move to Throwback Thursday. We have a doozy of a question for Throwback Thursday. Wait till you see this one. Okay, anyway, how could they have made this question in 1 second question? They could have said x is 3 and y is equal to this crazy quadratic. Okay? Look, it's minus 3. Doesn't matter what this thing is. X plus 9, right? Okay, here, I know, Seth, you like we go thin, thin, thin. So basically the same thing. X is 3 is this line. And a parabola, or no matter where the parabola is.
Oh, yeah.
And wherever the parabola is, it could be here.
Yeah.
It could be here. Yeah. It could be here. Any parabola you want, any parabola in the world, the answer would be one solution. And this would be this would be a 10-second question.
Right. Well, let me give a variation of that. Okay, I'll be blue. Suppose there's another variation.
That's another variation.
They could say like y. Come on, you silly computer.
I know it's sluggish.
Yeah. What they could have said y equals negative 100.
Okay, y is negative 100. Yeah,
that's x equals no. Yeah. And then no, here's a variation. They use y. Now y equals this thing. Yeah.
Wait, what?
Yeah. So I think what I'm saying is what I'm thinking of here is at y equals negative 100 and the same as before.
Yeah,
y
so there's no answer. So there's no answer.
Yeah, y equals 2x minus 3.
Right. Yeah, it's the same.
And times x minus 9.
Right. So there's no solution.
And in this case, the answer would be there are no real solutions.
That's right. Because the line y is equal to negative 100. Here, we'll move it back to our little graph. Oh, I knocked the graph out. But okay, fine. No. So remember before.
I'll do it. I'm doing it in blue. Here is the parabola. Oh, sorry.
Yeah, that's good because that's negative 55.
No, the vertex is a negative side.
Yeah, it's like
So it's like this.
Right. This is 55 down.
And then the line. This is the parabola. Of course, it's parabola shade, and then the line would be way down here.
Right, exactly, and there'll be no solution to it. Right. Yeah, don't forget. So the equation, if this is important though, equation of a horizontal line is y is a number, The equation of vertical line is x is a number. That's really important to know, right? That's important to know. Yeah. So this would be no solution. If
the linear equation has both x and y with non-zero coefficients, then the line is slopey. It's not vertical and it's not horizontal.
It's called a normal line.
Let's call the line in general position.
Fine, a line in general position. So I would love to have been an ant or a bug on the offices of the people who wrote this question, because I wouldn't be surprised if they were considering these two options to make it a little faster. So we'll see. I would think they had a debate. I would think they thought about it. I think the person who wrote this at least thought about it. Which of these three options are they going to give?
Yeah.
Okay, ready for Throwback Thursday?
Yes.
So
let's go. Throwback Thursday.
Seth has we're going to reveal a big secret. It's not a big secret at all. That Seth has a PhD in what's called combinatorics, which frankly I don't quite understand. I said I understand. It's counting. It's counting. So now, my God, his counting problem. Now, I just say a prayer every day that the modern SAT post-2016 doesn't have questions like this. This is not my type of thing. You have to be really smart to do this. I mean, having a PhD in combinatorics helps. Now, it's probably easier than I thought, but I always find problems like this intimidating. So, Seth, why don't you do it, and I'll sort of try to do it in my own head while you're doing it. Notice that this is nothing like you'd ever see.
Okay, so here we are. So the set, I'll read it. 6 points are placed on a circle, right? And the question is, what is the greatest number of different lines that can be drawn so that each line, presumably the different lines, passes through 2 of these points? Okay, so I don't know. Having learned, studied, wrote some papers in combinatorics over a period of how long? Maybe, 50 years. I don't know. Leads me to the solution very quickly. The idea is.
Seth, can I interrupt just
the idea is, though I could say it very quickly, but I'll discuss it for the benefit of our audience.
Seth, wait, no.
What should I do?
Seth, wait. There's nothing to do with the question. We forgot to tell everyone what Throwback Thursday is because there may be people who are new to this. Throwback Thursday is on Thursday. We go back 20 years to a test that was given about 20 years ago, to show you questions that they stopped giving on the modern SATs post-2016. So that's what Throwback Thursday is, and this is an exact question. Okay, Seth, go ahead, because something might not be right.
Okay, so, let's see. So they ask for, what is the greatest number of different lines so that each line passes through 2 of these points. Okay. Well, and they say the greatest number of different lines. So, I don't know. So, let's imagine, some of the points is 6 of them. 6 of them placed just arbitrarily on the, let's see, 1, 2, 3, 4, 5, 6. What is the greatest? Let's try to find lines that go through 2 of the points. So, here's a line. It doesn't go through any of the points, so they're not interested in that. And here's a line.
It's very sluggish. It's not showing
that goes through 1 of the points, not 2. They're not interested in that. Here's a line that doesn't go through any of the points. Not interested in that. We could have another kind of line, a tangent line, that goes through only 1 of the points. They're not interested in that. So there you darken the 6 points, but for every pair of lines, every pair of points, there's a single line that goes through the 2 of them. Now, if the points are distinct, is it possible for one line to go through 3 of the points? No. No way. Why? Geometry? Well, what's the geometry? That if 3 points are not in a line, there's a unique circle that contains the 3 points. But anyway, so it looks like the answer to this question, to get a set of lines, each of which goes through exactly 2 of the points, what you do is look for all the possible unordered pairs of points. Each pair of points determines one of these lines, and they're all different. So one of the things that's taught in some classes is that the number of ways of picking 2 things out of a collection of 6, without regard to which one you pick first and which one you pick second, is the binomial coefficient. So here I have 6. It's written 6C2. It's also denoted 6 with over 2 in parentheses. In English, it's read 6 choose 2. And a topic in some math classes is that this is equal to, like this. You take 6, multiply it by the next number down, and then stop because of the 2 here. You pick 6 and the numbers below it for as many as the number in the denominator, and you divide that by counting up to 2, multiplying 1 times 2, and so we get 30 over 2, which is 15, and so the answer is 15. Now, should I tell them why this formula gives you the number of pairs of points out of 6? Should I explain that?
Well, yeah, this is the classic committee problem. So what you've done is you've taken a complicated problem that doesn't look like it's the classic committee problem of choosing given 6 people, how many ways can you make a 2-person committee? Yeah. And you've realized that the problem is the same. And so it's interesting, right? You took a really good problem-solving technique. You took a problem that didn't seem like it's a committee problem, and you mapped it into the committee problem. Yeah. And the reason why it's no order doesn't matter is because this line going this way is the same, counts as the same as this line going this way. So that's why order doesn't matter. So
okay. So you get the maximum. So you always get 15 lines when the 6 points are all different. The logic of this is that the statement of the problem does not rule out that some of the 6 points might be the same point.
Don't go there. Stop.
No, I think that's because it says 6 points are placed on a circle. They might be in the same place.
Yeah, but they're saying the greatest number, so you have to be general.
Yeah. So the thing is, what misled me is a somewhat different problem.
Yeah.
It goes like this. Here's a different problem.
The different problem. So this is Throwback Thursday. We'll just stick to this problem.
Okay, we'll stick to this one. If this problem is from the point of view of combinatorics, this is a very easy problem because you get the same number of lines, the same maximum number of lines, whenever you have 6 different points on the circle.
Right. Yeah.
Okay. And then that number is the solution to the committee problem, where the job is to, out of 6 people, how many different committees of 2 people can be chosen.
Right. Okay. Now.
Okay.
Okay. Let me just have a make a thought about this. Since the number is 15, this problem can also be done literally through brute force. It can be.
Ouch.
You can literally count it.
Oh yeah.
You could do
absolutely.
1, 2, 3, 4, 5, 6. You don't do 7. 8, 9, 10. 10. Oh God.
No.
Oh wait.
No. Don't do it that 10. Way. Do it systematically.
Wait. Okay.
I thought you was doing it systematically, but go back, erase the yellows, and do it systematically. 1,
2, 3, 4, 5.
Okay, stop.
Okay,
now, do all of the lines that start here and go to a point other than
I thought
the first one.
That. Oh, I wasn't doing it?
No.
Oh, that my brain was foggy. Okay, so that's 5. 1, 2, 3, 4, 5. Here we go. 6. I froze. Wait 6 seconds. No, it's painful.
From here to here.
I know.
You don't see it.
6, 7, 8, 9.
Yeah.
10, 11, 12, 13, 14, 15. Right. There's the answer. Yeah. So right. I would think that most people, if people had enough experience with probability and counting things, like the committee problem, there's a chance people would do that. Probably most people would just do brute force.
I don't know.
We don't know.
I don't know. My thinking is that if you knew about the committee problem, you would solve it by reducing it to the committee problem. If you never heard of the committee problem, you might have the insight to count it by brute force. And the strategy that works for counting it by brute force is to do it systematically. You find all the lines that begin with point A, and then find all the lines that begin with point B, but do not go through point A, and then all the lines that go through point C, but don't go through point B or A.
Yeah, because you can.
And then you figure out that those that go through A, there are 5 remaining ones. Through B, there are 4, 5, 1, 2, 3, 4, and you add them. 5, 4, 3, 2, 1. 5 plus 4 plus 3 plus 2 plus 1 equals 15. Why? Yes, it added up and it works out. Yeah.
Right. Most people would just do it in their head like I was doing.
Yeah. You could imagine the committee. We'll label A, B.
We can do. So
A, B, C, D.
Force, fine. So we'll have 5.
No, you could solve the committee problem by brute force.
Yeah.
You have the possible members of the committee.
Right.
There's 6 of them. Imagine that they're joined in a circle. You break the circle, and then you say all the committees that contain A. There are 5 of them. All the committees that contain B but don't have an A. There are 4 of them. All the committees that contain C but don't have either A nor B. There are 3 of them. and those that contain D, but neither A, B, nor C. There are 2 of them. And then all the committees that contain F and none of the previous people, there's only all the committees that contain E, but none of the people previous to E in the circle. There's only 1 of them. You add them up and you get 15.
So that's it. So this is the committee problem done through brute force also.
Yeah. Well, so let me tell them how they derive the binomial coefficient formula.
Okay, wait. Now, this is a goodbye for everyone on Throwback Thursday because some people have just had it already with us. So we've already gone 40 minutes. This is like crazy. So anyway, let's say goodbye to everyone. See you later. You can hang on for the additional after party here where Seth's going to talk about the binomial theorem. And have a great day. See you tomorrow. And email us, of course, like us, dislike us, give us comments on our videos, and send us your math SAT questions at SAT Math Question of the Day. Have a great day, and you can hang on for the after party if you want to hear about the discussion of the binomial theorem. Don't ask a combinatorics person a combinatorics question because he or she will go on forever. Okay.
Okay, here's how. So, again, imagine you're forming the committee. One way of forming committee is to pick one person first. Pick one of these. And then after putting that person's name in this little box here, you then pick one of the remaining people. So if you suppose you picked C here, you then pick another person other than C, A, B, not C, A, B, C, D. I omitted C, D, E, F. Pick one of these. Well, there are 5 choices for this choice, and having made one choice, there are 4. There are 4 remaining choices. Okay. Now, so no, 6. I meant these are 6. There's 6 people, so I made a boo-boo there. Yeah, so the number of choices for the first person to put his name on the left is 6. And then to put the second person's name on the right, there are 5 choices. However, suppose the committee you picked this way was CA. Well, you could have gotten the same committee by picking A first and then C. Right. So there are 2 ways. So this count of 6 times 5 is an overcount by a factor of 2. Right. And so if you divide it by 2, you get the number of committees. Okay? Right. Now, why do we write it 1 times 2 there? Well, the answer is if you did it if you suppose you were picking a committee of 3 people out of 6, what you would do is pick. You have 6 choices for putting the name in the left-hand box, 5 choices for writing the name in the second box, and 4 choices for writing the name in the third box. And then you'd have, say, say AFE is one of these choices. Well, how many overcounts there are? The overcounting factor is the number of ways the committee of A, E, and F, well, you don't care about the order, the number of ways these 3 letters can be written in a sequence, in an ordered sequence. Well, the number of ways you could write these three letters in a row, the number of ways to do that, well, how many is it? There are three ways to pick the way the first one will be written. And then after picking the first one, there are two ways for picking the next one, whose name to write here. And then there's only one person left, and so there's one choice. So in general, this number, 3 times 2 times 1, would be called 3 factorial. And the factorial of a number is simply the number, let's do 8 factorial. 8 factorial is the number you get by starting with 8 and multiplying by all the integers below 8, all the positive integers below 8, 8, 7, 6, 5, 4, 3, 2, and 1, and multiplying them all together, which is a pretty humongous number. The factorial of 8 or n counts, the number of ways of rearranging, in this example, 8 things in a sequence, and that's called the number of permutations of 8 things. So in the case of the points or the 2-person committee, the number of ways of lists of putting 2 committee members in order, first and second, is 2 factorial, which, following the pattern for defining factorials, is 2 times 1. It comes about because there are 2 ways of picking the person to be put in the first position. And then, after picking the first of 2 people for the first position, there's only one person left. And so there's only one way to pick him. So that's the story of the factorials.
Okay, is that
it? That's it.
That's it? Okay, good. I thought you were, and don't do it. Don't do it. I thought you were going to come up with a derivation of the binomial theorem, but don't do it. Don't do it. Don't do it.
No.
Okay, that's it. We're done. Okay, yeah. Thanks, Seth, for that discussion about the committee problem. Anyone who is teetering on not understanding the committee problem, that hopefully that helped. Okay, everyone. We already said goodbye to everyone, so that's it. We'll see you tomorrow, hopefully. That's what we're planning on. Bye-bye.